Hello, hello. Today I'm going to try something a little bit different. This is not a Sudoku. I'm trying to think about, I've been trying for a while to think about other types of puzzles that I might be able to do here. Um, and I'm having a hard time. This past week, I found out that um, an old puzzle column that I used to do is kind of still exists, even though I thought it was gone. So 538, which I guess is, but it's not quite as relevant now as it used to be, is still a um, website that deals with forecasting in U.S. sports and politics. Anyway, they used to have a Friday column called the Riddler, where they would often have puzzles that were usually related to probability and statistics, but sometimes other math related or logic related puzzles. And I used to love that column. At some point in my life, I fell off doing them regularly. When I one day thought of it again and went to try to go back, I saw that it was gone. But it turns out there's still a weekly newsletter describing new puzzles every week. So I thought maybe I'd give one of those a try today. Let me know well, a couple of things. Is this kind of streaming something that you want to see? Are there other types of puzzles besides Sudokus that you want me to do? I mean, I don't think this is going to take over the Tuesday, Thursday kind of Sudoku slots, but anything that might be an additional puzzle that you'd want to see, let me know. And I'm actually recording this on Friday as the puzzle came out, but I think I'm going to hold the post until Monday because there is, I guess, technically a submission. I don't think there are prizes for the submission. I don't know. I haven't looked closely enough at what happens with submitting the answers to the Fiddler. But in case there's some type of integrity of a contest or something, I'm going to hold the post till Monday when the solutions come out. So what is the puzzle? The puzzle talks about three siblings that are all trying to get home, and they have a set speed. So Alice, which I'm going to call A for the purposes of explaining everything, takes 10 minutes to walk home. Bob, which I'll call B, takes 20 minutes, and what's the C? Carrie, which I'll call C, takes 30 minutes. And they can walk home, but they can be carried by each other, right? So, for example, A can put B on their back, and they will both essentially walk at A's speed. And they can put each other down, change directions. That doesn't take any time to do any of that stuff. So I read this morning, actually, in my email, and I've been thinking a little bit about it before doing this puzzle. So I'll try to walk through what I've thought. I haven't been able to put pen to paper or anything yet, and I think I'll be able to do it all in a spreadsheet. But if it gets too complicated, I don't know. Maybe I'll just turn the video off and try something else. But so the way I was thinking about it is, what is kind of an optimal strategy to try to get home for A, B, and C? And the first thing you might think of is, and the first thing I thought of was, well, A can just put C on their back because C is the slowest, right? And then A can kind of walk home with B at B's speed, and that would take 20 minutes. And that's kind of the first solution you might think of. But it seems to me that there are clearly better ways. So namely, A could walk home immediately, right? Take C there and drop them off. And if they did that and then wait for B, right? But instead of waiting for B, what A might do is instead walk back to B, pick B up, and then bring B home. And that should be a little bit faster than waiting for B to get home. I haven't done any calculations, so I don't know how much faster than 20 minutes it'll be, but it'll be somewhat faster. And then I thought, well, actually, they could do even a little bit better than that, right? A doesn't have to take C all the way home, right? You could shave a little bit of time off by dropping C off like a minute from home, or I don't know what the right number is, but some slight distance from home, so that A doesn't have to walk quite as far before turning around to go get B and then bring B home, right? And you could think about ways to like optimize that so that C would get home at the exact same time that A carrying B would also get home. And then I thought, well, maybe there's some type of leapfrog thing where, A could take B some distance, bring them forward, drop them off, come back and get C, and then bring them forward, and so forth. And I think what I've decided in my head is that doing this leapfrogging is not actually optimal because, or it's not optimal. It's no different than doing the version where they all get home at the exact same time that I explained a second ago. And the reason I think that is, well, suppose that it could be faster, right? Or let me think of it differently. Suppose that instead of getting home at the same time, they get, half the way home at the same time. Well, how long should that take? And basically, to make that work, you're going to end up going exactly half the distance to drop either B or C off. The A will drop B or C off before going back to get the other, and then meeting them like exactly at halfway. So if you're doing half the distance, if all those distances are halved, you should end up taking exactly half the time to get to the halfway point. So there's no benefit to kind of going back and forth. It all kind of scales fairly linearly. So the only question I still have in my mind is whether it's faster for A to take B some way, have them walk, then go back and get C, and meet them at home, or whether they should take C. And I'm guessing, there might be, my initial thought is that it won't matter which way you do it, but I'm not 100% sure. So I'm going to try it both ways and actually see what's better. I can imagine a situation where the time that they're walking is slightly different. And so you want B walking for longer than C, because A is going to be carrying one of them for the first leg and then going back to get the other one. And so the first one they carried will be walking, and the second one that was walking before will not be walking at the end. And so there might be some time differential that might make it, but I'm guessing it's going to all cancel out. But I haven't thought carefully enough about it to know that for sure. In fact, I think the easiest way is just to try it both ways and see what happens. So how do we actually go about doing this? So I think I'm just going to put some speeds up here, and the columns here are helpfully labeled. So I'm just going to write the word, speeds is showing up. Great. But I guess I should do it over here because then I can have A's speed. And so what is A's speed? Well, I actually don't know their speed. I only know how long it takes. So I have to assume something about how long they're walking. And I think it's not going to matter what assumption I make about how far they walk. Everything will just kind of scale to the time that it takes to walk. So I'm just going to assume that the distance that they're walking is 1. No units, just 1. And so A, if I do 1 over 10, that'll be the speed that A is walking per minute. B will be 1 over 20. And C will be 1 over 30. So these are my speeds for A, B, and C. And then I'm trying to think about how best to do this. So maybe I'm just going to make a grid that says what is the time, and at what time, like where is A location and B location and C, like where are they on this? If you think about A, B, and C being on this unit line going from 0 to 1, unit line segment, I guess. Like where are they going to be at different points in time? And I think I'll just do check-ins at certain, it's like, here I can do like what's happening, right? So time 0, everybody's at 0, right? So that's the start. And then what's kind of the first thing that happens is A is going to carry, let's say that A is going to carry B first. Again, I don't think it's going to matter. I'll try it both ways. So let's say A carries C somewhere and drops them off. So what's going to happen in that time? Well, first I have to decide how far they're going to be sent. And I actually don't know how to do that. I don't know how to do that. So I'm just going to make a silly assumption and say they take them, I don't know, 2/3 of the way. Let's make the math easy. So let's make it 3/4 of the way. I don't think it's going to be right, but in fact, I think it's going to be too far. But let's say they take them 3/4 of the way. So A and B will get 3/4 of the way there. So then I'm going to try to put over here, well, at what time will that happen? So what time will it be when A gets to 0.75? Well, it's just going to be the distance they are here divided by the speed that A walks. Right, so it takes 7.5 minutes to get 3/4 of the way there for A while they're carrying B. Then here I'm going to put, okay, where is C going to be at that point? Because C's just going to be walking by themselves. So they're going to be, I guess I'll do 0 plus, even though here I don't really need to. So how far along they're going to be? So for 7.5 minutes, walking at a speed of their speed, they will get, I guess, a quarter of the way, which makes sense that their speed is a third of A's. So that's where they're going to be at that point. And then what happens? A drops B off. So A is going to walk back to C to pick them up, right? And how long is that going to take? So I think the thing to do next is figure out what time that will happen. So now I need to be careful and say, well, it's going to be at whatever time we were at a second ago. We're going to add to that how long it takes for A to get to C. So how do we get that? Well, that's going to be the distance between them. That's A's location minus C's location, right, at the start of this process. And now I'm going to divide that by the speed that they're walking towards each other. But since A is walking backwards and C is walking forwards, I can add their speeds together to get the total speed that they're, like the relative speed of them going towards each other. So at this point, we're at 11.25 minutes. And now this is going to be a good check. I can do A's location and C's location separately, and hopefully they'll be at the same place, right? So what's A's location going to be? It's going to be that. They're walking backwards, so I'm going to subtract the time difference, right, which is hopefully A meets C at 11.25 minutes, and they started this process at 7.5 minutes. So that time difference times the speed that they're walking. So they get to 3/8 of the way there. Now hopefully C will also end up there. That looks like it's about right. So they're going to start at 0.25. They're going to go forward by the difference in time divided by C's speed here. Oh, I did something wrong. No, sorry, times C speed. Times C speed. Yeah, so they're at the same spot at this point in time. And where's B going to be? Well, they're going to keep walking towards home. So they're going to be wherever they were plus that same time difference times B's speed. So they're almost home now. So this is almost surely too big. I'm going to change this to equal A, and then I can change this, and everything will kind of automatically update with the formulas I'm doing. But for now, let's just keep it at 0.75. I'm going to shrink it a little bit. Well, that's nice. This might be right, actually. Anyway, well, let's try and see what happens. So A walks back to C to pick them up. And then let's see. And then A will carry C home, and hopefully right when B arrives. So what time will that happen? So so we're starting at 9 minutes for this process. How much time do we have to add? Well, it's the time for A to get home. So that's 1 minus where A starts divided by A's speed, 16 minutes total. And so where will A be at that point? They'll be here plus the time difference times A's speed. They'll be at home. And now where will C be? They'll be in the exact same spot. In fact, I'm just going to do equals A because C is being carried by A. I could do the same formula, but that's not really useful. So C is being carried by A. Now where is B? Now I'm thinking this 0.6 is probably not right, but let's just do the math. They're starting at 0.75. I'm going to add to that the amount of time that they're walking times B's speed. Oops. Times B's speed, right? B1. And that will get me to 1.1. So they went a little too far. So this is not going to be optimal. I can probably change this a little bit to make it a little bit better. So if I drop them off a little, if A drops B off a little bit earlier, then B will have a little bit more time to walk to do it. So what is the amount that I can do it? Like I could just guess and check here, but I want to think about a way that I could do this a little more formally. Oh, you know what? I think the way to do that is instead of getting A to carry C home, let's say like A catches up to B. Right, A catches up to B. And when is that going to happen? So now it's not going to be this isn't going to be 1, right? They're going to go, the time it's going to take them is, they're going to go not 1, but they have to catch up to B's spot. So that's this, they have to cover this distance. But now instead of dividing by A's speed, I'm going to do A minus B's speed. So why A minus B's speed? That's essentially the relative speed of A and B. So A is catching up to B by their difference in speed over time. And they have to catch up by their initial starting distance. So I think that's right. So A won't catch up to B until they get to 1.2. So in order to make, then what I want is for A to catch up to B right when they get home. So right when this gets to 1. So to do that, I basically need to divide this by the ratio of 1 to 1.2. So if I divide this by 1.2, that's actually 0.5. So if I put a 0.5 here, they'll get there exactly at 1. It'll take 15 minutes. So if I do it this way, where A carries, oh, did I do this backwards? Yeah, A carries, I did this, I just wrote it incorrectly. A carries B somewhere, and then A walks back to C. It's just, I just wrote this one incorrectly. So sorry, if you were confused because I did that wrong, I apologize. A's carrying B somewhere at the start, and C's walking at the beginning. And then A drops them off, whoops. A drops them off here, and then walks back to C. And this is, so when A gets back to C, A and C are a quarter of the way there, B is 5/8 of the way there. And then A is gonna walk back with C and get back home at exactly the same time that B does at 15 minutes. Now, what happens if I go the other way? So if I just do the exact same thing, but instead of A carrying B, instead A carries C. Now, I was going to say they should carry them the same distance, but I don't think that's true. Like, even if they end up being, even if this strategy ends up taking the exact same amount of time, which my hunch is it will, I think the distance that A will carry C is further. And in fact, I think it's going to be this distance. So I think, right, A went back to 1/4 of the way there to get C and carries them the whole way. I think they're going to have to, I think A at some time is going to have to get to 0.75 with C, drop them off, and then go back and get B. Like, I think if I'm right that it's symmetric, then what's going to have to be true is A is going to have to pick up C and carry them the same distance in both versions. So let's try it this way. And maybe I'm wrong, it's not really symmetric and we'll get a different, this one ended up at 1. And so it'll actually be shorter or faster this way. Anyway, how long does that take? Well, it's just the distance they go divided by the speed at which they go. That's 7.5 minutes. And then how far can B get in that time? Well, it's the time it takes times their speed. So they're going to get 3/8 of the way there. And then, A drops off C, walks back to B. So how long does that take? We start at 7.5 minutes. I'm going to add to that the distance A has to walk, which is the difference between A's location and B's location. That's not quite right. That's not actually the distance they walk, but it's the distance that the distance that A and B jointly need to travel to meet each other. I'm going to divide that by their joint speed. Like, how quickly are they closing that gap? And that's how long it'll take for them to meet. That'll be at 10 minutes. And then A is walking backwards. So by 10 minutes, they're starting at 0.75. They're going to go backwards. For this length of time, the difference in times A's speed. And hopefully B gets there to the same spot. So B is going to go forward by the difference in time times B's speed. Good, same spot. And then C is going to keep going forward at their speed. Yes. Cool. So then what's going to happen next is A takes B to C. And so how long will that take? Well, A has to catch up to C. They have to gain on C by this distance. So from 10 minutes, I'm going to add the distance that A needs to catch up to C, and I'm going to divide that by their difference in speed because they're walking in the same direction. So the relative speed is the difference in speeds. I did something wrong here. 11 plus B minus D, that's positive, divided by, what did I do wrong? Oh, wait, hold on, let me just erase it. So I did something wrong, but I can't tell what. So start at this time, I divide it by, so I add to that the difference in distance, which is that distance, divided by the difference in speeds. What am I doing wrong here? Let's look at so this must be -5. Why is that negative? A minus C is positive, and B minus D is positive. So why is that negative? Why is B minus D positive? Oh, got it. Sorry, I thought this was 0.08333 for some reason. Yeah, sorry. C is ahead of D, so I have to do it the other way. Sorry about that. So add to that, it's this distance. I should just use absolute values to be more careful, but I'm just not going to. A minus C here. So they will catch up at 15 minutes, and hopefully that will happen at 1. So it's going to be at 1. So this plus the time that A is walking times A's speed, right? And now B is being carried by A, and C should end up at the exact same spot. So they walk for 5 minutes times C's speed, they're also home. So yeah, 15 minutes is how long it will take either way. And that is that. Now, the bonus question, I have time to try the bonus. Add a fourth sibling. Maybe I have time, I don't know how long this is going to take. Add a fourth sibling that takes 60 minutes. So if we do that, so what's useful about doing this and showing myself that it doesn't matter which way it goes is that I think it's going to help us with the other problem too, because right, you might think there are so many ways to think about this problem with 4 siblings, right? Like A could take D somewhere, and B could take C somewhere, and then A could kind of, whatever happens, A is going to be like shuttling the siblings to each other to be carried. But what's useful is realizing from the first part of the problem that it really doesn't matter if A takes B somewhere and then goes back to get C and then meets them somewhere, or if A starts with C and goes back, right? As long, like, it really doesn't matter which way you go. So now when you add D, the real question is, so obviously at the start, D is going to get carried. And the question is D going to get carried by B or C, or is D going to get carried by A, right? I can imagine a world where, well, I don't think this is going to make sense. Maybe like A could carry D somewhere, go back and get B, bring them to D, and B will carry D some way, then A will go get C and then go get home. I don't think that makes sense. So I think the only plausible best paths are for A to take B or C somewhere, drop them off, and D is getting carried by the other. And then A will go back to the other 2 siblings, take D to the front sibling, like the forward sibling, and then go back and pick up the final sibling, and then everyone meets at home. And because of this, I'm pretty convinced that it's not going to matter whether you start with B or C. And I'm convinced enough that I'm not going to try it both ways, at least for the video. So yeah. So let's try that. So let's erase. I'm going to keep this actually. We'll do it again. We're going to add a new speed, which is D speed, which is 1/60. And do the same thing here. Time, A location, B location, but now I need a new D location. And what's happening is over here. So at the start, everybody's at 0. And then at some point in time, let's stick to 0.5 for now, although I think it's going to have to be closer. So let's just try 0.3. I don't think it's going to be right, but we'll try 0.3. And let's say that A starts by carrying B. So A carries B somewhere, drops them off, and we'll say that C carries D. So how long is this going to take? It's going to be the distance A travels divided by A's speed is 3 minutes. How far can C get in that time? Well, it's the 3 minutes times their speed, and D will be in the same place because they're being carried by C. So A drops B off and goes back to pick up D. So I have this strategy. I'm actually not perfectly satisfied myself that it's definitely optimal, but I don't know how I would prove that it's optimal or that there's a better way. So what I'm going to say is I'm going to try this, see how long it takes. If you watching this come up with a better path, leave it in the comments. Let me know if you can find something better than this. But we're going to go through the calculation and see how long this takes. So how long is that going to take? So so we're going to start at 3 minutes. I'm going to add to that the distance A has to travel, which is A's location minus C's location. Divide that by the relative speed. And since they're walking towards each other, that's adding their speeds together. So that's going to get to 4.5 minutes. And where will A be here? A is going to go backwards for the distance and time we have between these points times A's speed. And C will be walking forward. So hopefully these will be the same. Times C's speed. And D's, yeah, the same. D's being carried by C, so they're going to the same spot. And now where will B get to at this point? B is going to start at point 3, and they're going to go forward for delta time times B speed. Okay, so now A will shuttle D to B is what's going to happen now. So how long will that take? Start at 4.5 minutes. How many more minutes will it take? It's the distance A has to go. So A has to catch up to B. So they have to close on B by this relative distance. And the relative time is the difference in their speed because they're walking in the same direction now. And so that'll take to 9 minutes to get to that point. And where will they be at that point? So A will go forward by the difference in time times the speed. And hopefully B gets to the same spot. That's pretty far. I wonder if I did something wrong, but hopefully that's right. Sorry, times not divided by. Okay, good. So I keep making this mistake of times divided by, right? So the general formula, right, is that speed is, speed is, I guess I can't just put an equal sign. Speed is the same as distance over time. So if I want to know something about the speed, I take distance divided by time. If I want to know something about the distance, right, that's going to be speed times time. And if I want to know something about the time, that is going to be distance divided by speed. So that's kind of what I'm doing. Oh, you can't see anything that is wrote there. Can I put these here? No, still too far. Oh, shoot. Here, let me just zoom out a little bit. I'm realizing that you're not seeing any of these things that I'm writing in the what's happening column. Where's the zoom? So hopefully that's not too small to read. And I can put these now over here, say. Oops. Right, so if I want to know speed, it's distance over time. If I want to know distance, it's speed times time. If I want to know time, it's distance over speed. That's just from the definition of speed being distance over time. I'm rearranging that equation for the thing I'm solving for. Anyway, so where is C at this point? Well, D is easy. D is being shuttled by A, so they're wherever A is. C is going to keep walking forward. So from their starting location, you get a delta time times their speed. And now A goes back to get C. And so how long will that take? Again, A has to go, it's the time we start at, plus A and C have to meet each other. They're starting at a distance of 0.3 apart, so that difference. So I'm going to divide that by the relative speed, which is the sum of their speeds since they're walking towards each other, at 11.25 minutes. And so where will everyone be at that point in time? So A is going backward, minus the difference in time. So they're 2.25 minutes. A is walking 4 times A's speed. B just keeps walking forward, so that's plus the difference in time times B's speed. C is also walking forward, so difference in time times C's speed. and D is being shuttled by B. So D is wherever B is. And then A catches up to B. When will that happen? It's you start at this time. How much more time do we need? It's that difference in distance divided by the relative speed, which now is the difference in their speeds because they're walking in the same direction. 18 minutes. Actually, this looks like it might be about right. We'll see. That's probably not exactly right. So A is going forwards by the difference in time times A's speed. Ooh, not quite. It's a weird difference to be off by, though. B is going forward too. So times by the difference in time times B speed. And C is being shuttled by A, and D is being shuttled by B. So to make this correct, I need to change my initial assumption about the distance. So this is 1 instead of 1.05. So 1.05 is 21 over 20. So I'm just going to take this times 20 over 21. And I get really ugly numbers, but I think it's right. So I think that's right. And that's my best guess. So thanks for watching. If you have a better solution, post in the comments. And if you want more videos of weird math riddles like this, let me know. I could probably try doing these fiddlers every week. If there's another type of puzzle that you want to see, let me know that too. Again, I don't want this to take away from the Tuesday, Thursday kind of Sudoku schedule, but I want to do something else too. So this is what I have in mind. So have a good Monday.